All right, ever stop to think about those invisible forces that are just all around us? I mean, how can you slice a tomato with almost no effort? Or how does a giant steel ship weighing thousands of tons just float? It's all thanks to this one thing that's constantly shaping our world, even when we don't notice it. And trust me, by the end of this, you are going to see it absolutely everywhere. So let's start with something we've all experienced, right? In the kitchen. You grab a dull knife and you can lean on it with all your might, and you just end up squishing the tomato. It's a mess. But then you pick up a really sharp knife and whoosh, it just glides right through. So, what is really going on there? What's the secret? Okay, now let's flip that completely on its head. Think about a huge, heavy tractor rolling across a super soft, muddy field like it's no big deal. But then you try to walk across that exact same field, and you just sink right in. That just doesn't seem to add up, does it? How can something so heavy stay on top while something so light sinks? Well, the key that unlocks both of these mysteries, the knife and the tractor, is one single, really powerful concept. See, it's not just about how much force you're using, it's about how you're using it. And the answer, the big secret, is pressure. Okay, let's dive into the nuts and bolts of this. To really get what's going on, we've got to look at the core formula. It's actually super simple, but man, is it powerful. So, what is pressure, really? Well, the textbook definition is pretty straightforward. It's the amount of force you apply over a specific area. That's it. A better way to think about it is it's a measure of how concentrated that force is. Is it spread out, or is it focused on a single point? And here's the magic formula that explains everything. P equals F divided by A. Super simple, right? P is for pressure, F is the force, the push or pull, and A is the area you're pushing on. It might look basic, but believe me, the implications are absolutely huge. And this formula shows us something really, really important. If you want to get higher pressure, sure, you can push harder, add more force. Or, and this is the real game changer, you can make the area smaller. And if you want lower pressure, you can ease up on the force, or you can make the area a whole lot bigger. That relationship with area, that's the secret sauce right there. All right, now that we have the formula under our belts, let's go back and solve those mysteries we started with. This is where it all clicks. Okay, this sharp knife. The force from your hand is the same whether the knife is sharp or dull, right? But with the sharp one, all that force gets concentrated onto a ridiculously tiny area, the microscopic edge of the blade. That creates an insane amount of pressure. So much pressure, in fact, that it just slices right through the tomato. And the tractor? It's the exact opposite. I mean, it's unbelievably heavy, so that's a ton of downward force. But look at its huge, wide tracks. They spread all that weight, all that force over a massive area. The result? The pressure on any one spot of mud is actually really low. So low it basically floats on top instead of sinking in. Pretty cool, huh? Okay, so solids make sense now. Force over area. Got it. But what happens when we're not on solid ground? What happens when we dive into liquids? Does the same rule apply when you're underwater? Yeah, things have to change a bit, right? Because you can't really talk about the area something's pushing on when you're just surrounded by water. So, how does pressure even work when you're in a fluid? Picture this. You jump into a lake. Right at the surface, there's not much water on top of you, but as you swim down, deeper and deeper, the weight of all that water above you it starts to stack up. It's like you're holding up a column of water that gets taller and taller. The deeper you go, the heavier that column gets, and boom, the pressure goes way up. So this gives us two main things to think about for pressure in a liquid. First, as we just saw, is depth. That's a big one. The other one is the density of the liquid itself, basically how heavy or thick it is. Think about it. Swimming 5 feet deep in, say, mercury would feel a lot different than swimming 5 feet deep in water, because mercury is so much denser. And you guessed it, just like with solids, there's a slick little formula that lets us figure out exactly how much pressure changes when you're moving through a liquid. All right, here it is. Now, don't let the symbols freak you out. It says delta P equals rho g h. That little triangle is just a Greek letter, delta, and in science it just means change in. So the change in pressure equals rho times g times h. Let's break down what all that stuff actually means. Okay, so that delta P is just the extra squeeze you feel as you go deeper. Simple. That rho symbol, it looks kind of like a P. That's just density, or the heaviness of the liquid. G is just gravity, the constant downward pull from Earth. And H is the change in height, or put simply, how deep you go. See? Not so scary. So let's just boil this all down. What are the two big takeaways? For solids, it's all about area. Tiny area, massive pressure. Huge area, low pressure. That's the whole game. But for liquids, it's all about depth. The deeper you go, the greater the squeeze. Simple as that. And I want to leave you with one last thing to chew on. The air in the room with you right now, that's a fluid too, just like water. It has weight and it's pushing down on you right now. You are literally sitting at the bottom of an ocean of air. So think about that. You've got the entire weight of the sky, miles and miles of air, pressing down on you this very second. Kind of makes you feel small, doesn't it?